Okay. Uh, Last time we reached up to here, so let's continue. So the thermal resistance network. Now, in the previous lecture, we see how we deal with single resistance if we have conduction, convection, or radiation. Now, if we have a wall in this example, and from this side, uh, and from this side we have certain resistance coming from convection. Okay, here we have resistance coming from solid, which is conduction, our wall, and here we have another resistance coming from convection. So the flow of the Q will be in this direction. Okay, and here you can see analogy between electrical and thermal. Okay, if you want to compare. So this is the flow of Q. Now, every resistance, for example, here we have R convection 1, we name it, and this one we call it R convection 2. R convection 1 works between two temperatures, T infinity 1 and T1. Okay, R wall the same between T1 and T2. Okay, R convection 2 the same between T2 and T infinity. And if you can notice that three resistance are on parallel, on series, sorry. Okay, R convection 1, R wall, R convection 2. So the total resistance, if you benefit from the knowledge you have it from the electrical, so R total in this case, R total will equal to R convection 1 plus R wall plus R convection 2. Okay, and this is equal R convection 1, which is at 1 over H1 area surface 1 plus R wall L over K multiplied by K for whom, for wall, multiplied by cross sectional area plus 1 over R H2 or H convection 2 multiplied by surface area 2. This is how we calculate R total. Now, another important notice here that you must notice that if we are talking about current, then current passing through first resistance must equal the current pass through resistance 2 must equal resistance pass through resistance 3. The same for Q. Q pass through convection R convection 1 must equal R pass through R wall must equal R convection 2, which is equal to Q total. Okay, I will not name it as Q total, but you must know that this is the same Q. Okay, so we can say that rate of heat convection into the wall, Q dot convection, this is a Q dot convection, must equal to rate of heat conduction, Q dot conduction, because same Q, series. We are talking about series resistance. Okay, same as the current, nothing changed, equal to Q dot convection, and this is Q convection 2. Okay, and this one is 1. And this is equal to Q, just Q, or you can name it as Q total. Okay, so Q, this is the Q total, the same on each resistance. Okay, this we name it as R convection 2 and this is R wall, R conduction wall, and this is R convection wall. Okay, yeah, here it is. And see the junction temperature T infinity 1, this one, minus T1, okay, for the first resistance. Okay, very good. So the most important thing is that Q is the same on each one. So Q for the whole resistance, we'll say that T infinity 1 minus T infinity 2, this is T infinity 1, minus T infinity 2 divided by the summation or the total resistance. Because here we have series resistance, then the total resistance will be the summation of all resistance. And the unit remain as is. Nothing changed with the unit. Our total degrees Celsius over watt. So if I know the resistance and I know Q dot, then I can know delta T or temperature drop. We call it temperature, a drop through the wall from one side to another. Now, another terminology which is very important to know about it is the U. U, its name is overall heat transfer coefficient. Overall heat transfer coefficient, which is equal to, so Q total or Q dot passing through the three resistors. This is the Q. In the previous slide, we say that R total, okay, or sorry, in the previous slide, we said that Q equal delta T over R total. Okay, now instead of that, we can use U multiplied by area. Okay, multiplied by delta T. Delta T in this scenario is T infinity 1 minus T infinity 2, the two junction at the end, at the starting and at the end, okay? Because we are talking about the total. So in this scenario, U multiplied by A over all heat transfer coefficient multiplied by A must equal 1 over R total. And its unit is watt per Kelvin. U multiplied by area, watt per Kelvin. So the unit for U alone, so the unit for U is watt per meter squared multiplied by Kelvin or Celsius multiplied by meter squared, and meter with meter cancel out and we end up with watt Kelvin. Okay. Once Q dot is evaluated, once we know the magnitude of Q dot, the surface temperature T1 can be determined from this relation. Okay? From this relation. So if we know Q, maybe one of the questions will be like this. If you know Q by applying this equation or the previous one, which is here, I can write it, delta T over R total. Okay, if we know it from here, then the question asks about T1. So either we can come to T1 from this direction or from this direction. Okay. Now, if we come to T1 from this direction, let me go to solving. So here is the resistance. So here we have T infinity 1, and here we have T1, and here we have T2, and here we have T infinity 2. And sometimes the question come and ask about find out T1. T1 is unknown. Okay, T1 is unknown. So what to do in this scenario? We will say that Q is known because we calculated from U VA delta T or from delta T over R total. So if we know Q and we wish to come from this side, knowing that this is R convection 1. Okay, so we can say that T infinity 1 minus T1 divided by R, we have only one resistance, R convection 1. One resistance from this direction. Or we can tackle it from the other direction, from here, in order to reach T1. So if we use the other direction, we can write which is equal to, because Q constant along the among each resistance. So this is R wall, and here we have R convection 2. So we can say that because T1 is highest, so we'll start with T1 because the flow of the Q in this direction. Remember that. Okay, so we'll start from T1 minus, we are talking now about this scenario. Okay, T1 minus T infinity 2. How many resistance we have between these two temperatures? We have R wall and we have R convection 2. So both of them on series. So we can write R wall plus, because they are on series, plus R convection 2. Okay, so Q known, T infinity 1 known, R convection 1 known, so we can find out this unknown if we tackle it from this direction. Now if we tackle it from the other direction, this one, then T infinity 2 known, R wall, R convection, as well as Q, then we can find T1. So either from that direction or from the other direction. Okay, so here, so if Q is known, is evaluated from the previous equation, then the surface temperature T1 can be determined from this equation. This equation, you can tell me now from which direction we tackle it. Yes, from here. Because we start with this temperature minus T1, and between these two temperatures we have only one resistance, which is R convection 1. Okay. Here, if we have, so in the previous slide, we have only single wall. Okay, single wall. What will happen if we have multi-layer? Multi-layer means we have wall 1 and it has K1 as it's written here, and we have another wall made from another material K2, and this is the arrangement. So the first question, if this question come in the exam, draw the resistance network. So the resistance network will see the temperatures. So we draw T1, then first resistance, T infinity 1, sorry, then this is T1, another resistance from wall 1, another temperature here, T for the wall number 2, the surface temperature, which we label T3, and here we have resistance coming from convection or radiation or combination. Okay, so if this is the arrangement of the wall, okay, the resistance will be on series. So R total will be summation of all resistance. Okay, if the arrangement of the wall, put it like this. okay, beside each other. So Q total will equal to the starting temperature, the end temperature, T infinity 1 minus T infinity 2 divided by R total, and R total in this scenario, the summation. Now, we'll go back to our debate. So, if the question asks you to find, for example, this is T1, this junction T2, and here we have T3. So we ask about T2 here. So we can reach T2 from this direction or from the other direction. Okay, if we come from this direction, this is the equation. Okay, we know Q1. This direction will start with T infinity 1 minus T2. Here is T2. And between T infinity 1 and T2, we have how many resistance? 2 resistance, and both of them on series. So we'll add them. Or we can reach from the other direction. If we reached from the other direction, where is it? This is the other direction. So how we can write the equation? So we'll say that this is equal to T2 minus T infinity 2 over R between these two temperatures, which is R wall 2 plus R convection 2. Okay. So we'll do the same for the other temperatures. Here is a good example. We are care about T3. So if we care about T3, where is it? Here is T3. So T3 either from this direction or from the other direction. Which one is easier? Yes, this direction, because we have only one resistance. So we'll say that T3 minus T infinity 2 over R convection 2. Sometimes we are not looking for easier, we are looking for the most given information. So if T infinity 2 given, then we'll come from this direction. Okay. If T2 infinity 2 is unknown and everything in this direction known, so we'll choose this one. Okay. So it depends on the question. Thermal contact resistance. In thermal contact resistance, this is appear when we are talking about multi-layer. So here we have two examples. This is ideal or perfect thermal contact. Here this is the actual. This is the actual or imperfect thermal contact between two layers. So here you can notice that we have layer 1, wall 1, made from certain material, and here we have another material, layer 2, maybe will be made from same material. So if there is no surface roughness, then the two layers will be in perfect contact. So the Q will flow without any attenuation. Okay. ما بيكون في تكسير في انتقال الحرارة. But here, if we have certain roughness, imperfect contact, and this is usually what happens, okay, because of roughness, we'll have here gaps. Those gaps filled with maybe air, maybe vacuum, okay, so this will affect the Q. So the Q will not be flowing smoothly, okay. If you will go to here, for example, for the perfect, temperature keep it dropping until we reach the point of contact, then temperature will continue flowing. So there is no temperature drop. T1 will equal to T2. T from layer surface layer 1 at this position must equal T2 because this is perfect contact. Now, what happened in reality? So T1 at this side will be greater than T2. We have temperature drop. So we have temperature drop if we have imperfect contact. So the temperature distribution and heat flow lines, those lines, okay, along two solid plates pressed against each other. So this is what happened when we have two layers. We press them against each other. For the case of perfect and imperfect contact, here is the example on both. So how we press them against each other, here is the mechanism, okay? So we use this mechanism in order to press those two layers against each other, okay? When two such surfaces are pressed against each other, the peaks from good material contact, but the valleys from void filled with the air, okay? So here, let me go back to the previous slide. So peaks is something good, we need it, but valleys will filled. Here we have valley. This is let me erase everything. Here is valley. Then we have sorry. Here is peak, and then we have valley. Then we have peak, قمة وقاع. Okay. So whenever the peaks from the two layers meet, then this is something good. We have good contact. But whenever there are valleys, then this is something bad. Okay, this is the meaning of this statement. Okay, when two each surface are pressed against each other, the peaks form. Sorry, this is really good. Form good material contact, but the valleys form void filled with air. Okay, void. These numerous air gaps, because we are talking about certain roughness in micro maybe, so we have a lot of gaps, a lot of voids of varying sizes. Those gaps act as insulation, and insulation in certain application we need good contact, we need good heat flow, we need the heat to be conducted. So if we have certain roughness and we have imperfect, then we'll have insulation, which will affect the magnitude of heat conducted. Thus, an interface offers some resistance. So if we have two material pressed against each other, we have interface, and this interface either could be perfect or imperfect. So if it is imperfect, then it will offer some resistance to heat transfer. And this resistance per unit interface area is called thermal contact resistance. Okay, called thermal contact resistance. Now, thermal contact resistance, I will explain this terminology next lecture, inshallah. See you until then.